Bismillah ar-Rahman ar-Rahim. We have integral x from 0 to 1 log x log 1 minus x to the power 4 over 1 plus x squared. 1 minus x to the power 4 is equal to 1 minus x squared times 1 plus x squared. This integral is equal to integral x from 0 to 1 log x log 1 minus x squared over 1 plus x squared plus integral x from 0 to 1 log x log 1 plus x squared over 1 plus x squared. If we obtain this integral, and since we know this one from a previous video, we can obtain also this integral here and several others as we will see. In the video investigating this integral, we obtained these useful results. Integral x from 0 to 1 log x over 1 plus x squared is minus g. G is Catalan's constant. Integral x from 0 to 1 log x squared over 1 plus x squared is pi cubed over 16. Let's rewrite this integral as integral x from 0 to 1 of log 1 minus x to the power 4 d integral from 1 to x log t over 1 plus t squared dt. To do integration by parts, we need to take the limit of the product of these two functions of x as x tends to 0 from above and as x tends to 1 from below. When x tends to 0, there is no problem. We get an integral that is equal to g. It's multiplied by log 1, which is 0. We need to compute the limit as x tends to 1 from below of log 1 minus x to the power 4 multiplied by the integral. Note that from this result, and given that 1 minus x squared is 1 minus x times 1 plus x, we can write down this as log 1 plus x squared plus log 1 plus x plus log 1 minus x. When x tends to 1, the integral is 0, and it's multiplied by log 2 here. Log 2 there is no problem. We get 0. We focus on the limit as x tends to 1 from below of log 1 minus x times the integral. The integral tends to 0 as x tends to 1. 1 over the logarithm also tends to 0. We are in a 0 over 0 situation. Applying L'Hopital, the limit is the limit of the ratio of the first derivatives. The first derivative of the numerator is 1 times log x over 1 plus x squared. This is the integrand with the dummy variable of integration replaced by the upper limit of integration, x. Downstairs, we have minus 1 over the square of the logarithm multiplied by minus 1 over 1 minus x. 1 over 1 plus x squared tends to 1/2 as x tends to 1. Then we have the limit of the logarithm, which is 0, multiplied by the limit as x tends to 1 from below of 1 minus x times the square of the logarithm of 1 minus x. If this is 0 or any finite number, then the overall limit is equal to 0. This limit is equivalent to the limit as x tends to 0 from above of x times the square of log x. We can write this as the ratio log x squared over 1 over x. That's an infinity over infinity situation. We can apply L'Hopital a couple of times and show that this limit is 0. If we come back to our first step here, when we do integration by parts, the limits are equal to 0. The integral of interest is minus integral x from 0 to 1, integral t from 1 to x log t over 1 plus t squared. We should have here the derivative of log 1 minus x to the power 4 with respect to x. That's minus 4x cubed over 1 minus x to the power 4. Now let's write this integral as an integral from 0 to x minus an integral from 0 to 1. The integral from 0 to 1 is minus g, so we get plus g here. In the integral from 0 to x, let's use the change of variables t equal to x, y. When t is 0, y is 0. When t is x, y is 1. This integral becomes integral y from 0 to 1 log xy over 1 plus x squared y squared. dt is x dy. Take this 4 outside the integral. We have gx cubed over 1 minus x to the power 4. Log xy is log x plus log y. Each logarithm is multiplied by x times x cubed. I write x to the power 4 log y as minus log y between brackets 1 minus x to the 4 minus 1. This part here is equal to log y over 1 plus x squared y squared minus log y over 1 plus x squared y squared times 1 minus x to the power 4. This term, together with the term with g, are here. We also have these two other integrals. Let's start with this one. Let's integrate first with respect to x. The antiderivative of 1 over 1 plus x squared y squared is the inverse tangent of xy divided by y. Using the limits of integration, we get the inverse tangent of y divided by y. We have integral y from 0 to 1 log y over y times the inverse tangent of y. This is 1/2 integral y from 0 to 1, the inverse tangent of y, d log y squared. If y is 1, then inverse 1 is pi over 4, and log 1 is 0. We need to obtain the limit as y tends to 0 from above of the inverse tangent of y divided by 1 over log y squared. This is a 0 over 0 situation. We can use L'Hopital's rule to show that this limit is 0. This integral is minus 1/2 integral y from 0 to 1 log y squared divided by 1 plus y squared. This integral is pi cubed over 16. This integral here is equal to minus pi cubed over 32. We do partial fractions to 1 over 1 minus x to the 4 times 1 plus x squared y squared. Multiply by log y and integrate from 0 to 1. this integral can be split into these three integrals. Except for this minus sign, the integrand here is like the integrand there with x and y swapped. So these go away. This integral with respect to y is minus g. We get 4 integral x from 0 to 1 minus g over 2 over 1 minus x squared plus g x cubed over 1 minus x to the 4. We can take g outside, and this is the integral that we have. For this part here, the integral with respect to x is the inverse tangent of 1, which is pi over 4. The integral with respect to y can be obtained by doing the series expansion, then integrating term by term. Integral y from 0 to 1, y to the a, log y to the b is minus 1 to the b, gamma of b plus 1 over a plus 1 to the power b plus 1. Applying this result here, we get summation j from 0 to infinity, 1 over 2j plus 1 squared times minus 1. This is minus zeta of 2 times 3/4. That's minus pi squared over 8. Our integral of interest is pi cubed over 16 plus 2g, 1 minus x to the power 4. In the numerator, we have 2x cubed minus between brackets 1 plus x squared. Change this plus to minus. Multiply the numerator by minus 1. We get 1 plus x squared minus 2x cubed. Let's write this as 1 minus x cubed plus x squared minus x cubed. Downstairs, 1 minus x to the 4 is 1 minus x times 1 plus x times 1 plus x squared. 1 minus x cubed is 1 minus x times 1 plus x squared. X squared minus x cubed is 1 minus x times x squared. We have cancellation. This ratio is 1 over 1 plus x over 1 plus x squared. The antiderivative of this part is log 1 plus x. The antiderivative of that part is 1/2 log 1 plus x squared. When x is 0, both are equal to 0. When x is 1, we get log 2 from here and from there. Our integral of interest, x from 0 to 1, log x log 1 minus x to the 4 over 1 plus x squared, is equal to pi cubed over 16 minus 3 g log 2. As I said in the beginning, this is log 1 minus x squared plus log 1 plus x squared. If we subtract this integral from this one, we get the value of the integral x from 0 to 1 log x log 1 plus x squared over 1 plus x squared. The result is in terms of pi g log 2 and the imaginary part of the trilogarithm of 1 plus I over 2. We can actually obtain more integrals. We have these 4 integrals a, b, c, and d, used 2 times previously to evaluate the integral x from 0 to infinity, x over the hyperbolic cosine of x log 1 minus 1 over the hyperbolic cosine of x, and integral x from 0 to 1, the dilogarithm of 1 plus x squared over 2 over 1 plus x squared. In terms of these integrals a, b, c, and d, the integral with the dilogarithm function is equal to 2d minus c. The integral with respect to the hyperbolic cosine function was equal to 2c minus 4d, which is minus 2 between brackets 2d minus c. In the previous work, we obtained that 2d minus c is g log 2. We obtained this result by establishing these identities that relate the integrals a, b, c, and d. The good news now is that this integral we have just obtained is c. Using 2d minus c equal to g log 2, we can obtain the integral x from 0 to 1 log x log 1 minus x over 1 plus x squared. Here it is. Before getting a and b, since we know this integral, and from the previous video we have integral x from 0 to 1 log x log 1 minus x squared over 1 plus x squared. If we subtract this integral from that one, we get the term log 1 minus x squared minus log 1 minus x. That's log 1 plus x. We can now obtain this integral here. A is integral x from 0 to 1 log x log 1 minus x over 1 plus x all over 1 plus x squared. And this is log 1 minus x minus log 1 plus x. Subtracting this integral from that one gives us integral a. We have a previous identity. A is equal to 4b plus pi cubed over 16. B is a over 4 minus pi cubed over 64. We get b, which is integral x from 0 to 1 log x, the inverse tangent of x over 1 minus x squared. Now we have the 4 of them. In the work to obtain this integral, we also have these 2 results. There are 2 integrals here. We know this one, so we can obtain that one. Here, we know this. We know that we can obtain this integral, which has the same integrand like here, but the integral is from 0 to infinity. Here it is. By obtaining these two integrals and establishing identities relating several other integrals, we got all those results.